Hello everyone. In this video, I'm going to show you how to design a common base amplifier. Common base amplifier is very useful in the sense that uh, the high frequency behavior is much more powerful than the common emitter amplifier. And let's start. So I've already given the name of the circuits. So let's start with. To start with, you need a biasing circuit. So what I would do is to pick a NPN transistor, and you can pick any transistor that has low Muller capacitance. CJC is the Muller capacitance. So you need to find the one with very small CJC. So this one, 4 pico. There are many better ones. But this one is also okay. We don't need to scratch our head. We can change the transistor later if we need to. And another thing is we need to design a biasing circuit. So I will do this. I will choose a value here, say 10K. And this one is probably 1K. And then I will choose the ground here. Without the ground, it won't work. I will make up a low, say 1K. And the generator resistance, the emitter resistance, normally you start with a small value, 10 is enough. Now, you need a supply voltage for this circuit. So you choose voltage, and the voltage is a DC voltage. And I will use A volt. Now, the next thing that you need is to add an input and output port. In common base amplifier, the input is placed here. The output is placed here. So we add the input to the emitter. We inject the signal to the emitter. So we add a capacitance, and the purpose of the capacitor is to filter off all the DC signal. So probably 1 micro is enough. And you add the voltage source here. The voltage source is a small signal voltage source. And for the time being, before doing anything, let's skip this step. We don't add in anything here. For the time being, we need to check the current. we need to check whether there's enough current going to the collector. So the analysis that you need in the first stage is DC operating point. And this is the best way to check whether there is enough current. So if you stimulate the circuit, and you will get 3 milliamp. 3 milliamp is okay in many cases, but it could be too big. So you have to make sure the base emitter voltage here is small. You can either increase this voltage to make it small, or you can decrease this voltage. So if you do that, I will just increase this one here. So I will make it say 30. We will check the current again. So the current is 1 milliamp. 1 milliamp is good. 1.7 milliamp. 1.7 milliamp is good. It would be better if you can make it slightly lower. So I will increase the voltage a little bit further. Say 60. So 1.1 milliamp is quite okay. Then the next thing that you would do, of course, you don't need the next thing you will do is to add the voltage source at the output. So at the input. So you add it here. And the voltage that you need for AC analysis is this one here. So you add it here. You don't use DC. You need to tap around here to access this menu. In this menu, there are many options. The one that you need is specific to small signal analysis. It is small signal AC analysis, and the voltage that you need is probably 100 micro. 100 micro is quite okay. And the output is normally tapped in here. So I will just use and then we tap here. And you will use 1 micro as well. And you can do input here. And you need a low resistance. Normally, the low resistance should be much quicker. To start with, yeah, you use a large value compared to is large enough. It should be large compared to ROE. Yeah, I would rename this resistor. ROC is better, is more understandable because it is connected to the C terminal. Well, this capacity resistor should be renamed to RE. RE means the resistance connected to the E terminal. And I will put a ground here, and you do this. And the resistance that we need, as I said to you, probably 10K or 100K is better. And you are going to label the LED. For this one, you can label input in as an input. And for this one, out as output. And the analysis that you need is AC analysis. So AC, and if you want to the gain to be presented in decibel, then you should choose decade 100, yeah, the number of horns, and the starting frequency. The starting frequency can be just 1K. The stop frequency, right, as I used before, was 0.5 giga. So I just put it here, and you don't need DC operating point analysis again. So this is your shortcut. Let me see. Now there's another thing you need to bear in mind. First, you are using the shortcut using common emitter amplifier. The terms commons mean ground. So you are designing a common base amplifier. The terms commons means ground. This means uh, the base, yeah, common base amplifier means the base is ground. Okay, so you will put the capacitor here. You need a capacitor here so that all the AC signal will go through here. It will not affect the DC bias. It will only affect the AC. The AC signal, the high frequency signal, will go through the capacitor and reach the ground. And this is the purpose. So we will use 110. And now I'm going to move this a little bit up. So I presume this circuit is done. And let's see how it works. So now you end up with, after simulation, you end up with a waveform window. You position the cursor onto the waveform window and then right click, and you will end up with a pull down menu, and you add trace. You choose the option add trace, and you put the voltage gain V out divided by V in. So this is the voltage gain here. So here we go. Not too bad. We have a much wider bandwidth, and the voltage gain is also very high. And remember, the phase here will be close to zero in the um, in the pass band. It shouldn't be larger than 40. Yeah. If you want higher gain, yeah. If you want higher gain, what you can do is yeah, you can reduce the voltage here 0.5. Yeah, the bandwidth is wider. It's almost 100 megahertz, but the gain is lower. Yeah, there is always a trade-off when you try to decrease the resistance in whatever part you like in a circuit. There's always an engineering trade-off. I will just keep it like this. So this is the common base amplifier. Uh, I think the best way you can do to change the bandwidth here is to change the transistor. Let's say if we do this, so I end up with a slightly wider bandwidth. I just randomly choose one. But this is a power transistor. Let's try this. Power transistor, high gain, but very little bandwidth. Okay, not too bad. There's not much you can do. Anyway, thank you very much. If you have any question regarding this design, please leave your comments. Please leave your comment, leave your question in the comment section of this video. Thank you.